This playlist deals with some aspects of the Eurocode 2 version of 2023. Watch this playlist or this channel for further selected topics on the new elements presented in the Eurocode 2 version 2023. This video deals with clause 4 or some elements of clause 4, basis of design, and in more detail it will handle annex D about restraint imposed deformation. Concerning the partial factors for materials, when you look at the different limit states, we can determine the material factor for reinforcing steel, for concrete, or those two are for concrete. We see that for concrete in ULS, the ultimate limit state, the material factor is 1.5, which is like it is today. But you see also factor, material factor on the modus of elasticity of concrete. So this is also 1.5, so there's no problem. Only the code says now that gamma C can be 1.3 when confirmed by test. Having in a design phase, that's difficult to obtain the needed information to apply this rule of 1.3. That's for big projects. You at least, when the concrete quality is known or the concrete composition is known before you've done the calculations, so you can lower this material factor. A second difference is in the ultimate limit state accidental. The material factor for concrete is not 1.2 but 1.15. And then we have the material factor gamma V, which is a material factor concerning shear force. So if you are dealing with shear force, the material factor for concrete is not 1.5 but 1.4, which is new. In clause 4.2.1.3 states that the effects resulting from restraint imposed deformations should be quantified and considered when verifying serviceability limit state on fatigue. So this is for me very clear that restraint deformation is handled in SLS situation. But the code says that the effects of restraint imposed deformation may be neglected, its ultimate limit states that, only when it can be demonstrated that there is sufficient deformation capacity to allow the respective movements to occur and fulfill the ultimate limit state, and the structure behavior is not sensitive to second order effects caused by large displacements. So in principle, restraint deformation, you deal it in SLS, and when you have large displacements due to that effect, or then you should also look at the influence on ultimate limit state. Then the clause 4.2.1.3 says that for detailed analysis, you see annex D. So now we have a look at annex D. The cracking risk is the ratio between the maximum tensile stresses sigma CT and the tensile resistance of the concrete at the moment which is considered. So we take as a tensile resistance of concrete 80% of FCT effective at a certain time. This whole formula is defined at the time t, expressed in days. We do not know what is the value of t. It's something between 2 days and 28 days, for instance, but we don't know. It's not stated clearly what the t value would be to calculate this cracking risk. When the cracking risk is smaller than 1, then it's okay. The cracking risk is acceptable. When it's bigger than 1, then we should do something to minimize this risk. This is a short-term approach, so it's short-term cracking. So let's say t is between 0 and 28 days. The first problem, of course, is what time t should be used. We don't know. Maybe we should use time t equals to t critical, and t critical is the critical time for early age cracking, and it's the time at which thermal equilibrium with the restraining structure is achieved within 2 degrees, and the greater part of basic shrinkage has already developed. So this is in theory nice. It can be true, but what do you take when you want to apply the formula? We don't know. In a design phase, you don't know what the critical is. Now, when we take the tensile of the threads in the concrete in function of time, then you will see when the concrete is freshly poured that in the first couple of hours, the stress in the concrete is positive when there is restraint deformation, because there is hydration heat, the concrete wants to expand and creates pressure. So this is from T door until T2. So T2 is a time at which the first tensile stress develops until you reach T critical, and T critical is where the cracking risk is for the first time bigger than 1. All those values of T are not known yet, certainly not in a design phase. Formula D4 of the code says that sigma 1 equals what is written here. Now we will look at that in detail. First of all, we suppose, because we don't know, it's not stated in the code, that sigma 1 equals sigma CT from the previous formula of cracking risk. And we assume that the T equals T critical, which is there. So that's the first assumption. Then there is a term EC2, EC at the time T2. It's the modulus of elasticity of concrete at time T2, which is there. And the code says T2 may be replaced by maturity. What is this? Is it 28 days? Is it 7 days? Is it 8 days? What do they mean by maturity? And they say it must be corrected for the temperature history in accordance with formula B18. Now, you need a lot of information to use formula B18, and in most cases, it's not available. So for normal calculations, T2 is unknown. You don't know. So we have to deal with it. T2, the definition is the time when concrete starts to develop tensile stresses. There. And in most cases, because you do not have all the necessary data, you can assume that T2 is 2 days. So we will take T2 equals to 2 days. After 2 days, tensile stresses develop in the concrete. Now we will assume 2 cases. First, we will assume that T2 in this formula to evaluate the modulus of elasticity is equal to T critical, which means we are here, and we calculate at this moment the modulus of elasticity. And we will take another case when the modulus of elasticity is at time T2, because the modulus of elasticity is also a function of time. And somewhere between T2 and T critical, the cracking risk is high. So now, at what time is it? And for calculating the modulus of elasticity only at time T2, then you have a low modulus of elasticity. And at time T critical, bigger than T2, you will have a higher modulus of elasticity. So we will see what is the influence of the limit of this interval T2, T critical. That's why we define two cases that we will study for the modulus of elasticity. Further, we will investigate the different aspects of the formula. RAX is the restraint factor corresponding to the boundary conditions present after concreting. This is defined in a formula 9.14, which is stated here. But this is almost not practical to calculate. It's very difficult to calculate this shrinkage or strain, the imposed strain and the strain when the structure is restrained. This is difficult to calculate. Luckily, the restraint factor is something between 0.25 and 0.5. It's never bigger than 0.5. And most of the time, it's never lower than 0.25. So in most cases, you have an interval of 0.25 to 0.5. So what we will do is we will investigate this range of restraining factor, and this will cover most cases. Of course, there are also special cases where the restraining factor is 0, then you don't have any problem, or when the restraining factor is even 1, but that is almost not the case. TC max is the maximum temperature in concrete after casting due to hydration heat. From practice, we know that the maximum temperature in concrete after casting, that it of course depends on curing conditions, on weather conditions, and so on the it depends on how you put the concrete in place. But practice shows that the maximum temperature is between 30 and 70 degrees. It cannot be bigger than 70 degrees, otherwise the concrete will have some durability problems. So we know this limit is for sure, and this is also in most cases the case. So we will investigate the interval 30 and 70 degrees. In most cases, when you do a design, you don't know the maximum temperature in the concrete during hydration heat. So I recommend, if you don't know, use 60 degrees, which is more or less a maximum before you run into trouble. Then T0 is the temperature of the restraining structure. We don't know. So you see that a lot of elements in the formula to calculate the cracking risk are in fact not known at design phase. So, but what we will do is when the temperature of the restraining structure, we'll take it as 10 degrees. And alpha CPH is the linear coefficient of thermal expansion, which is 10 to the power minus 5. Then we have the strains, epsilon CBS, given by this formula. The beta term is a function of time. The alpha is an NDP factor. It's 1, or the recommended value is 1. And then ECBS FCM is a factor of the mean compressive strength of concrete, which is equal to FCK plus 8. It's also a formula depending on a coefficient, and this coefficient is dependent on the class of cement, the rapid cement, the neutral one, and the flow one. So then you have different values, alpha BS. Further on, we have the modus of elasticity, ECM, which is, of course, this is, we know we want to have the value of the modus of elasticity in function of time, because we will calculate it in the interval T2 until T critical. It's given by this formula before. And then this is the ECM, the mean modus of elasticity. And we take, in most cases, it's quartz-size aggregate, so we take the value of 9,500, FCM to the power 1/3. And just remember that the cracking risk was the tensile concrete stress divided by the resistant tensile concrete stress. And we said that FCTF can be taken as FCTM if nothing else is known. And FCTM is, of course, a function of FCTM and the beta CC coefficient. The FCTM is for concrete quality smaller than 50 megapascal. It's given by this formula, and for high strength concrete, it's given by this formula. And the beta CC factor, it's a function of time and Tref, and Tref is the reference time expressed in days where you define the concrete compressive strength. So in most cases, we define it at 28 days. But the code allows you to define this characteristic value of the compressive strength at other times. For instance, 90 days or 50 days or something like that, something in between. So that's why TREF is stated there. But in most cases, we take 28 days, and then this formula becomes a little bit more simplified. You still have the term SC, which depends on the concrete quality and on the class of cement. You have different values. Okay. Now with all those different formulas, we will now calculate two cases in the interval, the lower part of the interval and the higher part, which means in case 1 that T2 equals T critical for the estimation of EC2, with T critical equal to 7 days. No, we'll explain that later on. So we will take T2 to calculate the modus of elasticity, and at the time T equals T critical. Now, what we in fact want to do in the first place is what is the cracking risk in function of the time. So in that interval T2, T critical, we want to calculate for every day the crack risk and see what is the influence on it. Yeah? What do we take as T critical? We don't know. So we take a case and we say T2 is 2 days. That means that after 2 days, the tensile stress develops in the concrete. T0 is 10 degrees. The maximum hydration heat is 60 degrees. We take normal cement. The quality of concrete, we take 30 megapascal. And we take two cases. We know that the restraint factor is between 0.25 and 0.5. So we'll take those. We investigate those two cases. On the x-axis, you see now T critical. Remember, this was T2 and this was T critical, 28 days, for instance. Because otherwise you have a long-term approach, and this is another formula. So for the short term, T critical is somewhere between T2 and between 2 days and 28 days. Now we will investigate the cracking risk on each day. This is the cracking risk R critical. And we have two curves. We start, for instance, with the curve when the restraint factor is 0.25. And we see in this case that the cracking risk for this restraining factor is always bigger than 1. So if the cracking risk is more than 1, then you have to make some arrangements, put more reinforcement in it or something like that, or adapting the method of curing. So in all cases of C critical between the interval 2 and 28, you will always have a cracking risk bigger than 1. We also see that, for instance, for a cracking risk on restraint factor of 0.5, that after 7 days, the influence of the time in the formula is more or less neglectable. Means it's less influence. In the beginning, from 2 to 7 days, the influence is big on the cracking risk, but after that, it is more or less neglectable. That's an interesting thing because now we can adopt the critical equal to 7 days. So we say that the risk of cracking is the highest when after 7 days. We will now take case 2. And case 2 is that we calculated with the lowest modus of elasticity. It is the modus of elasticity after 2 days. Now again, we will, for the same parameters, we will calculate the influence. We have again the cracking risk in function of T critical. And we see now that for a restraint factor of 0.25, there is, after 4 days, no cracking risk. So that's interesting to know. So after 4 days, there is no cracking risk because it's smaller than 1. For a restraining factor of 0.5, it's more or less the same. After 7 days, the cracking risk is neglectable after 7 days. Now we rearrange formulas, and we are going to take again the two cases like previous one. But what we are going to do now is we calculate the maximum hydration heat that is allowed to avoid early cracking. In the sense of we calculate the maximum hydration heat where the cracking risk is smaller or equal to 1. And we do that for different cases. T2 is 2 days, T0 is 10 degrees. Maximum temperature, we take the interval of 30 to 70 degrees. And we take cement S, N, and air, R, and the concrete quality 30, 40, and 50, just to have a range. Now we make all combinations of those parameters and we calculate the maximum hydration heat for a given cracking risk. We can see that as a cracking risk, we know now or we investigate the range between 0.25 and 0.5 at a cracking risk of 0.5. You can, when you use all those different data input and you have the different curves, then you will see an interval, more or less, an interval, and it means that is an interval between 30 and 40 degrees for restraining factor 0.5. We do the same for the restraining factor of 0.25. We create an interval between 50 and 65 degrees. This means that at a restraining factor of 0.5, the maximum allowable hydration heat should be between 30 and 40 degrees because of all those different parameters. But we know that the hydration heat is almost always bigger than 40 degrees. So this means that you have always at the restraining factor of 0.5, you will have um, a risk, a cracking risk bigger than 1. So the question is, why should we calculate it when we know it already from the beginning? It will be bigger than 1. So that's something to think about. On the other hand, when you have a restraining factor of 0.25, at a restraining factor of 0.25, the maximum allowable hydration heat should be between 50 and 65 degrees to avoid early cracking. Okay, that is in most cases the value of the hydration heat, but you see that when it's bigger than 50 degrees, in some cases, depending on the cement type and things that you've got, you will also have certain cracking risk, but it's less. Now we take case 2, where we take the lowest value of the modal volatility. It's after 2 days. We take the same parameters. We look at the same graphs generated by all those parameters. Again, we look at the different intervals, but all those values, you can put them in a table, and the limiting values, which is indicated here, are calculated by interpolation. Of course, when I say that the interval for a restraining factor of 0.5 is between 40 and 45 degrees, you will see, in fact, it is 38 or something like that, and not 45, but 47 or something like that, if you look at the interval. So I just rounded it up for this, just to give a ballpark figure. And on the other end, you will see that the calculations are stopped at 70 degrees, because otherwise your concrete will not be fine. It will not be durable. So I made an interpolation here to achieve a restraining factor of 0.25. So it's an interpolation. Then you will see at the restraining factor of 0.5, the maximum allowable hydration heat should be between 40 and 45 degrees, something like that. So it means, again, even with this case 2, you will always have a restraining factor bigger than 1 when you will have a cracking risk bigger than 1 with a restraint factor of 0.5. And on the other hand, at the restraining factor of 0.5, the maximum allowable hydration heat should be between 65 and 80 degrees. So this is always okay when the hydration heat is less than 60 degrees. So you have a certain restraining that you can allow, 0.25, that's the maximum, in case that you take the lowest modus of elasticity after 2 days. Conclusion, there is always a risk of early age cracking due to restraint deformation when the restraint factor is bigger than 0.25. And the influence of T equals T critical on cracking risk is more or less negligible after 7 days. It means that you can take T critical equal to 7 days, because then after 7 days, the influence is not that big. And then a last point, if now the cracking risk due to imposed deformation does occur, when the cracking risk is bigger than 1, then you must limit the crack width to the value that is imposed by the environment. And the crack width may then be calculated according clause 9.2.3. And for members restrained at the ends, this formula applies. And for members restrained at the edges, this formula applies. And for early age cracking, RAX epsilon 3 is this. And long-term cracking, it is this formula. We will, in other videos in this playlist, we will give you some examples how to calculate the crack width according to 9.2.3 at restraints imposed deformation.